We are talking about spacecraft and stabilizing them. We're going to continue on that vein. We ended with dual spin. We were analyzing dual spin. This is finishing up dual spin. And the idea here is if you have some spacecraft, looks a lot like a box. The way that the book sets it up, I'll follow that so that you could follow along in there. And I think that was what, section 4.4. The axes, B1, B2, B3, we're just sort of arbitrarily picking some principal axes. So this is a principal axis frame, but we don't know, which one is the max, min, or intermediate. So here's my principal axis frame. There is an angular velocity vector. So let's just do that. And the idea is that the angular velocity vector, we wanted to stay close to some nominally chosen equilibrium, and then we're adding in small deviations. So this is a chosen equilibrium spin, and then these are deviations or departures. This is actually the current angular velocity. So a chosen equilibrium spin needs to be along one of the principal axes, right? Equilibrium. The only pure spin is along one of these blue directions for this object when we're in free rigid body regime of space. So we need to pick it to be along B1, B2, or B3. By the convention of the book, B1 was chosen. So this is that. So we would say this is omega E1 in the B1 direction, right? And then the little deviations, here's the deviations, because there could be some small deviations. We want to know how those deviations evolve. If they grow, then this is an unstable situation. If they don't grow, so maybe, and the best that we could get is that if we're a little bit off of one of these principal axes, it's just going to sort of rotate around. And that's what we've seen a lot in these videos that I've shown. Omega is blue. It's hard to see, but it's not exactly aligned with one of the principal axes. And so what you get is this sinusoidal rotation of omega with respect to that body fixed axis. I guess it'd be better to see it in a body fixed frame. This might be a little confusing because we're including what it looks like in inertial space. You can only get pure motion about one of the axes. Here's something spinning exactly about its major axis, right? This is completely stable. This is the major axis. So it's stable not only short term, but long term. You don't have to worry about energy dissipation. It'll just keep spinning. But often, due to constraints about how a spacecraft needs to be designed, where the instruments need to go, what will fit inside the rocket, you can't have the direction that you say want pointing at the Earth to be the maximum axis. So that's why the dual spin idea was created, so you could stabilize even things that are otherwise unstable. So like this situation, this is taking the object, its intermediate axis, right, which we talked about last time, like spinning your phone or the book or any shape. If you get it started spinning close to its intermediate axis, it's going to want to do some kind of weird flip. And then this messes up where things are pointing. And pointing requirements are really important for satellites. You'll notice omega, even though after this flip, the number 2 axis is pointing in the opposite direction, but omega actually went back to pointing toward the same direction in inertial space. And I know this is sort of mind-boggling. Like, and H is the total angular momentum. It's constant the whole time. This might defy intuition. How can I get something moving and tumbling, and yet total angular momentum is constant? Well, that is a mystery for another time. If you want to know more, I could say something, but that would kind of lead us off topic. It has something to do with internal torques. I'll just leave it at that. Mysterious. Okay, where were we? So we're talking about, we haven't yet added the dual spin part of this. So, right, you've got the angular velocity. And suppose we add a rotor So I have this rotor, right? This is just it's a flywheel. So very heavy ring or disc. I get it spinning. And the idea is for whichever direction I call the number one direction, I want this thing spinning about that axis. And the thinking is that I could then stabilize that axis, no matter what it is, whether it's the minimum, maximum, or intermediate. The real fun comes with stabilizing the intermediate axis, because otherwise it is not stable, not in the least. So we add a rotor or flywheel spinning, and this is key, with respect to the spacecraft about the B1 axis. So if I were to add in a flywheel, and it's not going to look very good, something like that, that's not bad. That's not bad. But this thing is spinning. So here's our flywheel. Big heavy thing that spins, right? That's it. And you might say, well, then, what, do I really want a big heavy thing that all it does is spin? That's kind of a waste of really expensive mass. I don't know, put instruments or something. Or make it just a part of the spacecraft that's okay to spin. For illustration purposes, we're just thinking it was a giant mass, but it could have things in it that are useful to the mission. So you add a rotor. It's oriented so that it's only spinning. Its main spin with respect to the spacecraft is about the B1 axis. Of course, it is otherwise attached to the spacecraft. So it also is going to do whatever the spacecraft does. But with respect to the spacecraft, it's spinning about the B1 axis. And we want to know, okay, now with all this, with this setup, that's the dual spin. The spacecraft is spinning because there's usually some, maybe there's a mission requirement. Would be something like spin about B1 with a certain speed. I don't know what that is, 120 RPM. Whatever the requirement is. And so to get that, yeah, what is that certain speed? That certain speed is what we've called omega E1. The equilibrium rotation speed about the B1 direction. And what we boiled it down to last time, we looked at evolution equations, which is just my fancy way of saying equations of motion or differential equations for delta omega, that little departure or deviation vector. So how is that changing? So we're just talking about the little deviation. And we have to assume it's small, because when we write these equations, there'll be times where we say something small times something small is so small we neglect it. This is typical whenever you linearize. So we got this. We found that omega, the first one, delta omega 1 is just a constant. So if it starts out small, it stays small. It doesn't do anything. It's just a constant. Meaning if we started out spinning just a little bit more than we wanted, maybe it's 123 RPM, well, then that's what we got. But the other two will tell us about the wobble around that direction, around the B1 direction. So what we ended up getting is that delta omega 2 double dot plus k delta omega 2 equals 0. And if you were to do the other one, it's the same equation. It looks very much the same. So this looks like a simple harmonic oscillator, right? Both, what do I mean? Both look like x double dot plus k x equals 0. So if k is negative, then you get exponential growth, meaning unstable. Otherwise, if k is positive, then you have sinusoidal motion, and we would call that stable. It means that omega 1 and omega 2 are just going to be sinusoidally changing. So there'll be some wobble around the direction you want, but not growth. It won't be unstable. What was k? K, the way that we wrote it that was nice, omega E1 squared divided by I2, I3, I1 minus I3 plus I omega S, omega hat. So that's what we get. So we sort of factor things out so that this omega hat is it's omega divided by little omega e. It's just the non-dimensional flywheel spin rate. What's I1, I2, and I3? So the total moment of inertia matrix. This is for the spacecraft, including the flywheel. We could write that as just I, and it's about the center of mass, but since kind of everything's going to be about the center of mass, I might not even put the subscript C. And because we've chosen a body fixed principal axis frame, I1, I2, and I3 are along the diagonal. I1 being the principal moment about the B1 direction, then I2 about the B2, and I3 about the B3. We don't yet know the ordering, so we don't know if B1 is the max, min, or intermediate. And that's important because that's going to determine what we pick. We get to pick the rotor spin rate, and the rotor can spin in the positive sense or in the negative sense. We want to pick a spin rate that stabilizes the mission requirement of spinning around the B1 direction. So to do that, we're going to have to pick omega appropriately. But let's first verify what happens if the rotor isn't spinning. So if, just based on this equation up here and this definition of K, stability of spin about the B1 axis requires K is positive. And in some sense, it's more stable the more positive K is. You don't want K to be negative, then it's unstable. So this is our K. So let's just verify what happens if we were to lock the flywheel so it's not spinning. That just means not spinning with respect to the spacecraft. We would have that omega is 0, so omega hat, the non-dimensional one, is also 0. And what would we get for K? I2, I3, I1 minus I3 times I1 minus I2. For stability, this is what we need. So we're basically just going to see, do we recover what we expect for the free rigid body? And if you remember, the maximum inertia case and the minimum inertia case were the ones that were stable, and the intermediate would not be. So for this to be positive, both of these terms in here have to have the same sign. That means we have stability if I1 is greater than I3 and I1 is greater than I2, meaning the axis that we're spinning about is the max inertia, or we could have it be I1 is less than I3, which makes the first term negative, and I1 is less than I2, which means I1 is the smallest, so the min inertia case. And the other case is just unstable. If I1 is the intermediate, meaning it's between I3 and I2, let me just say unstable, like K is less than 0, and that's the intermediate inertia case. So this is the same result we got with the plots the book calls pole hold plots. the motion on the sphere, all that spheres intersecting ellipsoid nonsense. It's not nonsense, it's really clever and cool. But to the untrained eye, it's just a bunch of crazy nonsense. Good. So we've covered what we already knew. This is, in some sense, the linear analysis that shows that stability or instability cases. Okay. So now let's look at the stability requirement if the flywheel spin rate is non-zero. So now not the free rigid body, but so we don't have our flywheel locked. The flywheel is spinning at some speed. We want to know, what does that speed have to be to stabilize, depending on different cases. So going back to the full expression for K and just rewriting it from above. So I've got it here to refer to. This was I1 minus I3 plus, this is the moment of inertia of the flywheel about that B1 direction. Omega hat I1 minus I2 plus I omega S omega hat. And I ran out of room, so I'm moving it over. So this is for stability. That's a way to spell stability. So how is this true? This is true, again, if both terms in parentheses have the same sign. So we could figure out what that would be. And it depends on some different cases. We could make some assumptions about the ordering, but it's probably better to just look at a specific case. So now we're going to look at an example. So we're going to consider an example case. I'm going to just sketch something. Here is the satellite. Got our B1, B2, B3 directions. And this includes a flywheel. It's spinning around some speed, omega. We've got this spinning in this direction. We want it to spin in that direction with omega E1. Our example case, I'll give you some inertias. Let's say that the inertia, and this is the inertias for, in some sense, the spacecraft, including flywheel, because it is attached. We're not thinking of them as separate. It's attached. So the total inertias in these principal axes directions, we'll just use some nice round numbers, 350 kilogram meters squared. I2 is 300 kilogram meters squared. I3 is 400 kilogram meters squared. The flywheel, which is contributing to I1, but we'll put it as well because it's important. The flywheel has a, let's say it's relatively small, so it's only 10 kilograms meters squared for inertias. Now, which axis is B1? It's got 350, so it's between 300 and 400. B1 is the intermediate axis. And the company knows this, or maybe you find out, maybe you were just given a shape and told, okay, figure it out. And so you come back, hey, it's the intermediate axis. So I'm going to have to do some analysis of this flywheel. And they're like, well, we're told that we want omega E1 to be some spin rate. We could write it in terms of RPM, let's say 60 RPM. Rotations per minute. So this is spinning rapidly. That's 60 RPM. Well, once per second. Okay, I guess it's not that bad. Depends on how, we don't know the physical extent. We're just given these numbers. I'm guessing it's on the order of, the thing is on the order of hundreds of kilograms and probably has the extent of 1 or 2 meters. I don't know. So we want that, but we still don't know what to pick for omega. So we need to go through this analysis here. If we've got, in this case, I1 minus I3 is negative. So this is actually negative. I1 minus I2 is positive. Okay, how do we pick this? Let's start with a positive omega hat. This might not be the only one, but it's going to be 1, I would hope. If we have a positive omega hat, then what do we need? We need omega hat to be greater than, I'm rewriting this first term in the parentheses. We need this to be greater than, and so I'm going to flip a sign, I3 minus I1 IWS. I3 minus I1 is positive. So this is what? 400 minus 350 is 50 divided by 10 kilograms per meter squared. All right, those units cancel out. I get my non-dimensional number. This is 5. Okay, so that'll satisfy the first one. The second one, because I1 minus I2 is already positive, that will also be positive. So I've got both terms positive. Both terms in the parentheses are positive. So that's one condition. So omega hat greater than 5, that works. That's not the only one though, right? I could have chosen the case where both are negative. If I go through that, if I want both of these to be negative, then the one I need to focus on is this right one, because this is positive. This first term, I1 minus I2 is positive. So I'm going to have to pick omega hat, so that becomes negative. Run out of room. Oh, I can just do this. Wow. Smaller on the screen for you. Sorry. What about negative omega hat? Well, looking at the second parentheses term, I would need omega hat less than I2 minus I1. I2 minus I1 is negative. IWS. So this is also going to give me, because the difference just happens to be, again, negative 50 kilograms per meter squared over 10. It's negative. It's negative. So this is negative 5. So that makes that negative. That'll make this term negative. This term over here, because I1 minus I3 is already negative, you add in something that's also negative, they're both negative. It doesn't always work out to be symmetric. Doesn't always work out to be symmetric. I know based on my examples, people will be like, I got +5. Does the other one have to be negative the same number? No, I just, because of the numbers that were chosen here, it just turned out that way. So this also works. Okay, so if we were to summarize, we could summarize this in a plot just showing what omega hat is. There's 0, and we know 0 doesn't work. That makes things fall apart. Here's a 5, and then here's -5. So I could color, blue's nice. Blue's a nice color. How about blue means good. So these are regions that lead to stability. And there's 2. If I didn't pick these particular values of I1, I2, and I3 so that the difference between the intermediate and the max and min was 50, then one of these would be closer to 0, which means it would actually be easier to spin in that direction. It might be the negative direction. I don't know. Here, we know that it's the intermediate axis. So if we had a spin of 0, this thing is unstable. So we would maybe say this is the instability region. This is typically what you'll get. I don't know what we want to call this. Maybe we'll call this omega A and omega B. And you want to be greater than omega B and less than omega A. This is for the intermediate axis case. And I could qualitatively show you what it looks like for the other cases. If we had the max inertia case, what would this look like? Well, the nice thing about omega hat is it's a non-dimensional number. For this, we would have, if I plot 0, I don't like where I put it. I'm going to move it. We would have both of these less than 0. Omega B, omega A. So we know that even if we don't spin, the max inertia case is stable. but you could spin for whatever reason. Maybe you'd want to be in this range less than gamma A. Okay. You could also destabilize the maximum axis if you were so inclined for some reason. I don't know. You could destabilize that, and then this thing could maybe wobble. Maybe it's a way to, an interesting way to cheaply point in a new direction. But we had said that, at least long term, the minimum inertia case is unstable due to energy dissipation because of vibrations in the structure. So the other case that's typically used when you've got this dual spin is the min-inertia case. I mean, so what am I meaning by max inertia case? This means that I1, and I have it, I'm doing it this way. It depends on exactly what you have. But for this case, that I1's the greatest, I2's intermediate, and I3 is the smallest. Then this is what it would look like. And an example min inertia case would be, I'll put I1 at the end of this line. And again, let's plot the line of omega hat. And we'll have both of these on the right side of 0. So both positive omega hat A, omega hat B. So you need to be greater than omega hat B and less than omega hat A. And in the short term, of course, like 0 is in the positive region because for short times, the minimum axis is stable, but due to energy dissipation, maybe long term. And long term could be a few orbits. If your spacecraft fails after a few orbits, I don't know if you'll be working on another spacecraft. But anyway, so you could stabilize it long term by using a dual spinner. So I could give you an example. It was used for the first time in the 60s. As you can imagine, there was a lot of interest in space stuff in the 60s because it was the new frontier. So there was something called TAC-SAT-1. I don't even know what it was doing, but it was the first satellite to spin successfully about its minor axis, or about its min-inertia axis. And I've got a figure. It's pretty big. So this is what it looked like in the clean room. They should be wearing gloves. I don't know what's up with that. Yeah, it was the 60s. They probably went and had a smoke after this. So here's the axis that they wanted to spin about. And you can just kind of see from its shape, it's the min axis. This antenna is the main part of it, and they wanted it to be pointing at the Earth, spinning at 1 revolution per orbit. And the cylindrical body down here was in some sense, the flywheel. And this thing spun at 60 RPM. And I guess to figure out why they picked that particular value, we'd need to know moments of inertia and things. But yeah, then this part pointed at Earth, 1 spin per orbit. And I don't know which orbit it was on, if it was Leo or what. But it was the first dual spin to stabilize the minimum inertia axis. Now, here's a scenario. Okay, we have a spacecraft. It's made of, I guess 7 things. There's a top flat plate and a bottom flat plate, and then 4 equal rods on the ends. So it's sort of, it all fits in like a 1 meter cube. It's not a CubeSat. CubeSats have to be like 10 centimeters. This is like a giant CubeSat. And if you were told the mass of all of these things, including the flywheel is rigidly attached, pointing in the B1 direction. So B1, B2, and B3 are principal axes directions. And if you knew the mass and dimensions of all of these things, you could calculate the total moment of inertia and the moment of inertia of the flywheel So you could get, say, I1, moment of inertia about the number 1 axis, I2, I3, even IWS, which is going to contribute to I1, but we also separately know what it is. And if the company, I don't know, Elon Musk, he says, I want this satellite to spin stably about the B1 axis with a rate of 60 RPM. And then you're asked, to make that happen, determine the complete range of the flywheel spin rates. I think you know enough to do that. It does take some time to think about, okay, if this plate, if this top thing is 100 kilograms, and I don't know, everything's 100 kilograms or whatever, then figure it out, use the parallel axis theorem. It is important that the flywheel is centered at the center of mass, and you can assume that. Kind of looks like it is. Yeah, maybe everything's an instrument, so all you need to know is its mass. You don't need to know what it does, okay? At least for now. So I think you can handle that scenario. All right, it's time to stretch. And then we'll get to, I think, gravity gradients.